Hello everyone, welcome to the third day of the course. We made it to the half of the course. I am proud to introduce right now to Eduardo Ceccarelli. I introduced him a couple of days ago. He's the director of the mass spectrometry unit here at IBR, and today he's going to talk about LiP-MS. That is a relatively new technique, but it's the combination of an old technique like limited proteolysis now combined to MS. There are beautiful things to do with these techniques, and Eduardo will go through it, I'm sure, very nicely. Thank you, Eduardo, for being here and for these amazing talks.
Thank you, Germán. I hope you have enjoyed your yesterday practices. I will talk about a methodology that to tell the truth, I will never perform myself, neither my group. We worked before with limited proteolysis, but we never tried this technique. But I found this technique really nice. I think it's a powerful technique. It doesn't mean that this methodology try to preclude other methodologies of proteomic analysis of interactions. So we will try to see how to detect folding, protein-protein interaction, protein small molecules interaction all at once. That's kind of a great task. So check limited proteolysis to do that. I will go through some kind of biophysical basic aspects. When you have a protein, it's possible to identify a resistant core to proteolysis. So if you have the properly folded protein and you add a protease, normally the protease only cut in some exposed places at a higher speed. Then if the protein fall down in structure or the protein disensemble and unfold, the protease will cut in pieces and then will cut in small peptides. By the contrary, if you have an completely unfolded protein, the protease will readily cut the protein in small pieces. So you can differentiate different forms if you add the properly amount of protease. So if you are smart enough to get the proper protease concentration, you will be able to differentiate the unfolded state, the native or the naked protein. And to tell the truth, you not only have internal cuts in loops and these kind of things, the protease also will chop the N-terminal and the carboxyl terminus. Normally, if they are exposed, it will be cut by the protease. So what happens if we have some kind of disrupting event, if we add something to the protein? As a matter of fact, this technique was applied something like 30 or 40 years ago. They have a kind of time that was heavily applied, then became techniques applied sometimes in some works, mainly with pure proteins. But what happens if you have a protein that is cut in two places, and then a complex is formed, and the complex cover one of the places where you get the attack of the protease, you will get a different peptide product when you add the protease. And it's complex maybe because you have two proteins that are bound together forming a complex, or maybe that you have a small molecule that induces a conformational change in the molecule, or maybe that this molecule is closing a site where the protease go in to cut the protein, or maybe that this small molecule affect an interaction that are already formed. That means maybe that you disrupt an interaction, or that maybe that you form a complex after you add the small molecule. So you know that mass spec can give you different information, so you can try to check cofactor binding, lipid interactions, interaction on subunits that have not been already identified. You can have a heterogeneity of complexes or different proteoforms that you know, that means conformational changes in the protein you are studying, or maybe some kind of transient interaction of conditional interaction topology that maybe a complex subunits may change the stoichiometry or the interaction with the complex. So all of these will give you a different proteolytic pattern if you're lucky, of course. That always you have to be lucky. You run experiments of this kind. So I will go more deeply in biophysics, and I hope you don't get upset for this information, but we are trying to see the formation of a complex. You have maybe two proteins, or maybe one protein, one small molecule. You know, the affinity of this process is defined by equilibrium constant that maybe defined as the Kd for dissociation constant, or Ka or Kf for the inverse constant. That means that you can calculate this constant by the concentration of the complex and each one of the ligands, and that means that any change in this relation will produce a change in the equilibrium. And what is important in this Kd is the result of two constants that are velocity constants. They are not equilibrium constant. There is them that are measuring the speed in which this process runs to this side or to this side, depending on the concentrations of, in the case of K-on, the concentration of P and L, in the case of chaos, the concentration of the PL complex. Why I'm talking about that is that for the same affinity constant, you can have different velocity constants. So you can have the same Kd, let's say 10 nanomolar, and with this same affinity, the results that you can obtain can come with completely different kinetics of a complex formation and complex disruption. You know, you can, for the same Kd, you can have these different K-on and K-off. That means that you, in the case of the blue complex, you have a quickly formation of the complex and a completely fast disruption of the complex. For a really low speed complex, you can have a slow formation that never reach all sites occupied, and in the case of a low concentration, and for a high concentration, you even are closer but not reaching the complex formation. But you know that when you disrupt the concentration of the ligands, the complex stay for a time because the disruption or the formation of the complex is rather low. So when we are talking of Kd, we are not doing all that we need to know to know if we can catch this complex in solution. It's important, the KD, but when you say, well, I have a complex that have a high affinity, I will see the complex. I say how fast this complex is formed, how fast this complex is disrupted, and what kind of technology are you using. If you are using a technology that is not in vivo, or is not pointing the complex in the solution, and you need to disrupt the complex, like say you are filtering the complex or you are precipitating the complex, probably you won't catch your complex if your complex is a quick one, speedy complex. Only as an example, you can have here different complex in which you have different KD and different K-on, and this is, unless it's stated, are seconds, you know. For example, let's see this, there is a really high affinity complex. If you are working with this complex and you have a 10 to the 8th K-on, you have only 100 seconds in which the complex is disrupted after you take away the ligands. So if you are looking for this complex and using centrifuge, the complex is bound to your antibody, you have 100 seconds in which the complex will disappear. Normally, we're working in this kind of affinity, so normally we are rather down the second of the velocity in which a complex is formed and it is disrupted. This is having two things, bad things and the good things. So I will tell you the bad. There is most of the complex that normally we search for, we will never appear in our samples. But we have a good thing that may always have in mind. The problem, you have thousands of interactions that are still need to be discovered. So if you work and you find a proper way to go for these interactions, you will discover thousands of interactions that are still not discovered, that are still uncovered because this situation. So we are just entering in an incredible world of interactions, and we are starting to get the first interaction of a real complexity of a cell. So this is a nice technology that is emerging and is easily explained here. You prepare your sample of interest. I will go then over problems of advantage of disadvantage of this technology, but let me go first for the basis of the technology. So you get an extract, then you, in this extract, you induce a phenomena like I add a drug or I add a compound that I want to see how this compound affect my proteome. Then I will run a LiP experiment as limited proteolysis experiment, and then I will completely digest. Well, I will do the right thing for, I will denature, I will modify the peptides by alkylation, and I will digest by trypsin. So if we have something that alter the first limited proteolysis step, you will have here a new peptide that may come for a digested peptide that is not originated by trypsin, and if you are lucky, you can identify this peptide and then to know what was the problem that you have with your problem, what your protein, what it changed. Of course, this is an exemplification for one protein, but you have the possibility using the nowadays proteomics, the quality of the Orbitrap technology of other technologies, to search for all the peptides, new peptides that appear or disappear in your sample, and try to analyze what your small molecule, your effect have made to your proteome. So even more, going a little farther, you can even, if you have enough capability to run samples, you know, because this is you need to run several samples in your equipment. You can even check the effect of a small molecule or a protein other or a situation in a progressive way, in a way that I add different concentrations of a binder, of a molecule, and then I check the effects on different proteins, so I can identify a high affinity binder or I can identify a low affinity binder. If I have made a previous experiment in which I just identify effects in one protein, I can check for that protein the affinity of the molecule that is doing the effect. So let me go quickly through some of the technical aspects of the methodology, because in some of the technical aspects you can then discover the problems and the advantage of the methodology. Well, always you have the problem of a protein extraction. Until now, this is a methodology that is working mainly with extract. So you have to take your tissue or your cells, you have to lysis, make the lysis, and then from the extract you have to check and to analyze the effect. This is a problem because you have to be sure that the buffers that you are using and your pH and your ionic force are not disrupting too much the interactions of your extract. It always will happen. So it's better to think that this is a methodology that will not replace others or will complement other methodologies to search for interactions. So this is not trying to, the author, and I think it's in that way, you are not trying to replace another methodology, it's a complementation, trying to get new information. So you have to define very well the buffers and the environment in which you lysis your cells. In some cases, you may think to add some caltrops or detergents, and it's always problematic work with protein in membranes because most of the protein in the membrane is protected from the protease, and if you use some detergent or some helper to take the protein out of the membrane, the situation that you have here is far away from the reality. And the other problem is that sometimes you have to add protease inhibitor for other proteases, because when you extract your proteins, if you are in cell plants, you will have the back wall broken that will release proteases. If you have a eukaryotic cell, you have lysosomes, there will be free proteases that will affect your study. So then you will have two samples, one that will be through LiP-MS, another sample will be totally digested with the trypsin treatment. So that means the sample is divided. One sample is treated with some molecule, And then you will have two samples for each. The one will be the totally digested sample, and the sample that is previously proteolytic digested by limited proteolysis, and then totally digested. So one of the more important steps is the limited proteolysis step, that at first you don't have any idea of where are the setup that you have to use to get the proper information. But you can start doing some kind of experimental approaches in which you have to choose your protease. Normally, is use a proteinase K that is a protease that is highly active and acts on the aliphatic and aromatic residues. But maybe for your studies, for your samples, it's better to try another protease. It's something that you have to search in your research protocol. So it is important to define which protease, and then to find the proper concentration and enzyme substrate ratio that should be carefully determined. Let's say it's not important to at first to a priori to know this concentration, but then you have to be cautious that you repeat exactly this relation in all your experiments. And it's important this, because if you go for a really low protease concentration for the LiP experiment, maybe you lose several proteins that are not cut or attacked. And if you go from a high protease concentration, maybe you digest a lot your sample, and some proteins are degraded completely and disappear of your system of detection. And another important thing is the inactivation of the protease. You have to be sure that the protease that you are going to use can be inactivated in a rather perfect way, because another way, when you perform the sequential trypsin digestion, if you have some remaining protease, like proteinase K, the whole sample will be lost. So in these cases, in the case of proteinase K, thermal inactivation is possible, but you have to be sure that you have a good content of your sample with the bath of 95 degrees that is used to inactivate the protease. And then you have a trypsin digestion. In these experiments, it's important to be sure that you have a full digestion. Because one of the problems is that we are trying to identify peptides that maybe not are the more important peptides of our study. Because maybe there is, the complex only is a fraction, and then of this complex only a fraction is digested by the protease. So you know that the trypsin doesn't like to have a lysine and a proline, and normally you have like a 10 to 30% of the sites of lysine that are not cut by trypsin. So in this, it's good advice to use lyse C first, that have the same specificity for lysine with or without proline, following by proline, and then use trypsin. And in some cases, it's not a bad idea to use a denaturan like deoxycholates that can be then clean of the solution, or to use some of the commercial surfactants that are friendly with the mass spectrometry, but to digest the protein. So, and then you go to the normal step of peptide cleanup and vacuum dry go to the. So this is only an example. It's not real data. It's a simplified to understand what we are talking about. So you have here data of myoglobin in his apo and holo form, and when you perform this kind of experiment in a complex sample, I don't get accustomed to to use I know an old guy. So the myoglobin is have this alpha helix that is affected by the prosthetic group binding. So when you have the heme bound to the myoglobin, this alpha helix is fixed and it's not available for proteolysis. But if you don't have the heme, this alpha helix is mobile and can be cut by the protease. So in this case, you have two peptides that are generated for the proteolysis of proteinase K that allow you to identify and differentiate the protein that is with the myoglobin, with the heme bound to myoglobin, and from the protein that is not with the heme bound to. Let me go back to something that I mentioned to you. One of the problem is that you will have peptides that are not tryptic peptides. So you have to talk with the guy that is made that will run the mass spec if he's not of your group, and telling him that he should identify peptides that may have only single charge peptide, and for identify the peptide should be allow the fragmentation of single charge peptides. There is something technically that means that you should, it's not a sample that you have to send it and say identify, because the guy will give you the tryptic peptides but will miss the peptides that are not tryptic, or maybe he didn't care doesn't care about these peptides. And you will have an important result here is that you will have an abundance decrease of fully tryptic peptide associated with the digestion of the proteinase K, or you will have an increase of peptides that are non-tryptic peptides that have non-tryptic termini that are coming from the digestion of the proteinase K. And these peptides are normally smaller and hydrophilic peptides, so you will have to be cautious not to lose the small peptides that are coming in the front of the running of chromatography. So I follow with that. Well, so what are the pros of the process? If you run a proper LiP-MS spec experiment, you will have a lot of data. So you will have to sit down, think and analyze, because you will have hundreds of proteins that are affected in a complex sample by this process. So you have to clean and to see which are the proteins that are interesting for us. But the advantage, you have many processes and many proteins, so you will see complex formation, interactions, and protein folding and refolding. I will show you briefly a couple of examples now. The information obtained is intensive. You have a lot of information. So it's a good idea to combine with other proteomic methods, maybe from your lab or maybe from another labs, and compare the information. And sometimes with method of structural studies, it's not a bad idea to see with a bimodal, whichever you use, and say, well, this is the structure of this protein. Why this protein is giving me this result? Why the protease treatment liberate this, let free this kind of fraction of a protein? In fact, the analysis is benefit from information from other methods. Another way, you have to check that the complex you are seeing are physiological relevant. If you have a protein that comes from a lysosome and there is binding to a protein in the cytoplasm, you have to take care that maybe this is not a good interaction. Another way, when you produce a lysis of a cell, you have a lot of protein that will unfold by the lysis. For the process of the lysis, you will have a lot of chaperones interacting with polypeptides. So you don't have to be fooled for the data and to take any data as true. The method is simple and applicable because any lab can do it, and the advantage that is fast enough that you can run several samples in parallel. For example, to put your concentration of protease in and the relation of a sample and protease, you can run 5 tubes at the same time, and then run and analyze the peptides that you get, and you say, well, here we don't have any difference from the sample without treatment, and we have some difference with the number 3, and we have a good difference with the 4, but we lost the difference with the 5. So in one experiment you can get a lot of information. Well, one of the problems is that, as I told you, the problem is that you are working with fractions of molecules that are doing some conformational chain, or are going through some formation of a complex. So for proteins that are in low concentration, and you only have the capability to detect a fraction of this sample, sometimes you may not see signals for protein that may be relevant. Sometimes you can't predict the origin of the observation made. Maybe that you are pointing some effect by, there is not a physiological effect, or that you don't know the origin of a change. You see the change, but then maybe you don't have the data to explain the change. And as always, you can have artifacts because you change the protein concentration that is inside the cell. You change the compartmentalization of the cell, and you add buffers and reagents that shouldn't be there, but are necessary for the experiment. So let's see, for example, this is a paper published this year that these guys decide to study the whole refoldability of the E. coli proteome. So what they did is they lyse E. coli, then unfold E. coli with hydrochloride, guanidine hydrochloride, then refold, and then use a LiP-MS experiment to check what are the refoldable proteins or the non-refoldable proteins. And they, this is more or less the experiments. You will have in the normal proteome places where the protease cut the properly fold proteins that you need to identify. This will be one of the samples. And then in the refold proteins, you will have the protein that refolds, so they will give you the same peptide pattern that the normally folded proteins. Then you will have the aggregated protein that probably, maybe they even have less sites available because they are aggregated. And you will have misfolded protein, they will have another sites, or partially misfolded or unfolded protein that will be mainly digested by the protease K. So I will not go, there's some problem with the text, but no worry. Don't worry, I can go through that. So these guys with this data have analyzed different aspects of this refoldability of the proteome and looking for the intrinsic capability of a protein to be refolded, and they check different relations at a proteome level. For example, how many proteins that refold are in multi-subunit complexes, or how many protein and single proteins that refold spontaneously. How you can correlate the level of chaperones with the refoldability of a protein. Let's say a protein that normally is folded by a chaperone needs to be refolded, the chaperone or not. For example, you can check domains that are folded better than other domains. Proteins that you detect that one domain was properly folded and the other domain not. Or how the cofactors affect refoldability, or if you are checking refoldability at after 10 minutes, after 1 hour, or after 10 hours, how the time of refoldability affects the refolding proteome of E. coli. That means that they probably ran during 6 months or 1 year experiment. They probably worked 2 or 3 years searching and analyzing data. I'm saying, I don't know how fast the guy worked, but that means you get the data. If your data is really good, then you have to sit down and go the proper informatic, proper literature and start to analyze the huge amount of data that you generate. And for example, this is another example of this year. There is try to analyze with this system the dynamics of the proteomes. So what is the idea? Is I will prepare proteomes from the same cell, but with different conditions of for example, growing conditions, or I will take a proteome and I will heat shock, or I will perform an osmotic stress on the cell and see how the proteome is affected for this external signal that I'm imposing to the cell. So in this case, for example, of course this is This is a complex article that I'm not going to go deeply on it, but you have all the proteins that have been identified that are modified by heat shock or osmotic stress in yeast, or heat shock or osmotic stress in yeast. But it's an interesting finding of this article is that the protein abundance have a low change when you submit it to the heat shock and osmotic stress to the cell, but mainly you have protein structure changes, folding and unfolding, proteolysis, interactions. So you can see here there is a map at the proteomic level, the change produced for using an external aggression to the cell. So finally, and I'm not going to go through this technique, but I want to let you be aware of other approaches. Probably we will have more approaches in the near future. This strategy uses the idea that you can make a thermal profiling of a proteome. And if you make a thermal profiling of a proteome, the thermal profiling lets you to know about interactions, binding. For example, a protein that have a prosthetic group sure will be or less or more stable, probably more stable. So you can check in a way that you check the proteome in some kind of thermal condition, and then you check again the proteome that have changed for some external situation, for some growing conditions, for some and you check again the thermal proteome. And the method I'm not going to. I take the forbidden button. It's like the auto-destruction. There is one that for the presentation, another for the presentator. Well, coming back. The idea is you take the sample, you perform different thermal treatments of the proteome, then you use separation methods, mainly, maybe tubes that can be filter tubes like, centripreps or whatever you want, or maybe centrifugation at low or high speed, maybe ultracentrifugation. Then you get the soluble proteins of a proteome, and you study which are the proteins that are survive to the thermal challenge that you have put on the proteome. So, and what is interesting is that you have different situation, physiological situation with the same cell. You get that these proteomes change, and this information is relevant and may be analyzed in a way that you can even compare. And this is a recent small review, or it's like checking the possibilities that say, well, you can compare the LiP-MS mass spec and the thermal stability, and from the same proteome, and integrate both data, and even more with some of the great analytic possibility, like cryo-MM. Using cryo-MM, you can check complex that you have detected for thermal stability or LiP-MS spec, and then see if these complexes can be found in a cryo-MM study. So maybe that the idea is not only to integrate different proteomic approach to see interactions or changes in the proteome, but also to integrate different biophysical methods to increase the capability to understand the complexity of a cell. That's it for today. Thanks.
Thank you, Eduardo. Questions for Eduardo? Mr. Blanco? Sofia?
Hi, really nice talk. Do you know if LiP-MS have been applied to drug discovery to find the target of antibiotics?
Well, this is one of the main applications of LiP-MS. As a matter of fact, there are a couple of articles, but as far as I know, had been also applied in pharmaceutical labs with no publication of results. Probably this is the person that have developed the method. That may be an interested person to invite to come to talk for the next year.
Also from Switzerland. She's Italian, but she's working in Switzerland, so we are having great proteomics from Switzerland. But I encourage you to look for the papers of Paola Picotti. Eduardo has prepared a folder with papers for you to share with us, and I know you have a lot of papers from Paola
Picotti.
Yeah.
All the things that I mentioned here will be in this folder, and other papers too. That's the same for the protein preparation, showing in a way that you can go to the original literature, and there is a nature protocol of LiP-MS that is very well described. There is a great paper of Picotti describing step by step how to do the. She likes to to promote her papers and the methodology.
Thank you.
Hi. Hola. Very nice talk. I enjoyed a lot. I have just a question. What kind of negative control do you have to perform in this kind of experiment? You need to do the same experiment in the absence of proteinase K?
Well, the idea that a fully trypsinase, no proteinase K sample is your control. So you have to have a sample that is identical to the sample that you have. That is not that is completely digested without going through the LiP treatment. But to tell the truth, if you read each of the papers, you have to adapt your controls according to the criteria of the experiment. You have to think very well what will be but normally you have to divide your sample in two. One sample will be treated with a compound, another won't be treated, and you will have two samples of LiP and completely digested proteins. So that's the idea.
Okay, thank you.
Another question for Eduardo? Thank you, Eduardo.
Thank you.
this was the last talk from Eduardo, but Eduardo is from here, so he's going to be around for the rest of the course if you want to ask him some questions. But before you leave the stage, we want to give you a present, like for all our speakers. This is for you.
That's good. Thanks.
Yeah.
Thanks.
Drink it
Great.
with responsibility. Thank you, Eduardo, for your amazing talks.
Thank you.